Okay, welcome everyone to this new series on Lie theory. So not Lie theory, by the way, it's Lie theory. There's a person, the person will come up in the next video, who was called Lie. What is Lie theory? So what do you expect from Lie theory? Lie theory is something that is very dear to my heart, it's very, very applicable. It's like everywhere. It's one of the big theories you eventually need to learn if you want to advance somehow. And it's always kind of mysterious a little bit from the beginning, but let me just make this clear why Lie theory is so important. Lie theory is important through its applications. It kind of appears everywhere. And the reason why it appears everywhere, in case you can't guess that already, is so what is something that is just everywhere, just really powerful, really useful, just appears everywhere? Well, linear algebra. Linear algebra is one of the key theories ever developed by humans. Absolutely fantastic, absolutely powerful, appears everywhere. And Lie theory is like linear algebra with a little twist, if you want. Linear algebra plus. So somehow it's not too surprising that it appears everywhere as well. And in case it wasn't clear, if you don't know what linear algebra is, then this video series is probably not for you. If you don't like linear algebra, which is different from knowing what it is, right? And then this video series is probably also not for you, because I want you to have fun. I want you to, well, in principle, of course, you could just learn Lie theory without liking it, but I want you to like it, right? I want you to have fun. And kind of the point is the following. Let me just make this very clear. So linear algebra, very powerful. So, but there's also kind of the opposite side of it. It's not just that linear algebra is powerful, it's also that everything that goes beyond linear algebra, we don't really understand what's going on, yeah? So linear algebra, good, everything beyond, who knows? So that's why a lot of real-world applications, and I'm talking really about particle physics, if that is a real-world application, we will see some more real-world applications as we go along, but something like that, they try to model everything using linear algebra. Literally because, not because everything is linear algebra, but literally because it's the only thing that we can really understand, right? So we're not doing very well in the grand scheme of things. Everything non-linear, not great. Lie theory, linear algebra plus, so that's why it appears everywhere. Linear algebra, people always try to use linear algebra. For the obvious reason, as I just said, let me repeat it. I know I sound like a broken record, but let me repeat it anyway. For two reasons: it's super powerful, and everything beyond, we have literally no clue what's going on. Maybe I shouldn't say no clue, but compared to what we know about linear algebra, it's not all that great. So let's have a look at what is Lie theory. So what is Lie theory? Can we put this on one slide? We can, probably can. So to the left, on the left, is what is not Lie theory, and on the right is what is Lie theory. So Lie theory is essentially the mathematics of continuous symmetries. I always say continuous symmetries, but what I mean is smooth symmetries. Don't worry about the difference for now. Right, on the left, a discrete symmetry, a threefold rotation. So a rotation by 120 degrees. On the right, a continuous symmetry, the symmetry of the circle, where you can just rotate by any angle you want. Yeah? So continuous versus discrete, right? Now, one of them takes only 3 values, and the other one takes a continuous family of values. On the left, what people mathematically use to model the left are finite groups, and what people mathematically use to model the right are Lie groups. And that's not quite where they originally come from. As I said, there was a person named Lie who was very interested in the continuous groups. Will not appear in this video, will appear in the next video. But this is like the motivation I'm trying to use here in this video, right? So the study of continuous symmetries. And there will be two main players. So as I said again, the left side is not what we are doing, but the right side is what we are doing. So there will be two main players, Lie groups, usually a capital G, which is like the global object, the global symmetry. And it has an infinitesimal version, right? It's smooth now, so you can now take derivatives. It has an infinitesimal version, a derivative, the Lie algebra, which people usually denote by a small mass frac, a fracture type G. And the slogan throughout Lie theory that you always want to keep in mind, it's kind of fun. It's kind of a fun mixture between algebra and calculus. Linear algebra and calculus, maybe the only two things that really work, is to differentiate the symmetry and then integrate it back whenever you need. That's literally what you do. So Lie group is your symmetry, and the small g, the algebra, is your differentiation of the symmetry, and you can integrate back if you need to. So that's kind of the slogan of Lie theory. Okay, so continuous symmetries. I will give you more details as we go along, of course, but for now, this is all we need to know. So the examples I want you to keep in mind, essentially the only examples I have anyway, and essentially the only examples the theory has, it is more general, the theory is more general, but the only examples we really need are matrix groups. Yeah, orthogonal rotational symmetries, so special orthogonal groups, special orthogonal symmetries, general linear groups, special linear groups, just matrix groups. Yeah, just matrix groups. They're groups, and they also describe continuous symmetries and similar friends. It's kind of the main zoo. So that's literally linear algebra, right? So the groups, matrices. And yeah, I'll say it again, matrices are very powerful. Linear algebra is great. So this is where this whole thing comes from, right? The matrices, a collection of numbers that you can, in this case, multiply together. Yeah? And why matrices? Well, matrices. Why not? It's very concrete and easy to work with. As I said, the theory itself is more general, but the main focus, the main examples, the key players, the way this theory is developed is along matrix groups. So there will be a main focus of this series as well. And yeah, so let me just, why care? Here's my favorite picture of a Lie group, which I think of as a continuous thing, and of a Lie algebra, which I think of as a linear algebra thing. And the maps between them is you can differentiate and integrate, essentially. Sometimes called the exponential map, which goes in one direction, the logarithm, which goes in the other direction. And yeah, so this is the picture. You have continuous symmetries, like rotational symmetries of a sphere. And by magic, this absolute magic, you can describe them using a very, very linear object, the Lie algebra itself. So this is like this compression tool, which makes this theory so accessible. Lie algebras turn nonlinear groups, a sphere here, or here in this example, a circle, into questions into linear algebra. Linear algebra. Everyone loves linear algebra. Everyone loves linear algebra is actually true now, because I told you in the beginning that if you don't like linear algebra, then this video is not for you. So hopefully you have turned off, and now everyone likes linear algebra. So compression tool. Why is it so efficient? Because you can describe everything, these continuous funny symmetries, using linear algebra, and we'll see essentially it's linear algebra plus a bracket. That's essentially what it is. And that's a non-linear object, and you describe it without too much loss of information. It's kind of magic, using a linear algebra tool. And yeah, so actually this whole thing is then unreasonably efficient. Yeah, so it's you can argue, well, it's beautiful, it's nice, it's wonderful, I like it, it's fun. That's all good. I totally follow you, but this is kind of very subjective, right? An objective reason why Lie theory is so good is that it is just efficient, really efficient. Yeah, and it's kind of fantastic. So the picture that always kind of confused me is the first thing you learn in groups, actually the finite groups, and you think they are much easier than the Lie groups, but in reality the Lie groups are much easier than the finite groups. Finite groups are very random. They do very random things. Lie groups are very, very well behaved groups. This is what makes it then unreasonably efficient. And then kind of the same type of effect that turns up for as try to explain, try to mention or mentioned before, is whenever something is really efficient, kind of people try to use it all the time because it's a tool that is just efficient to describe things. I'm not saying Lie groups describe the world. I'm not saying linear algebra describes the world. I'm saying kind of the converse. The world, the way how we understand the world is modeled using linear algebra. It's modeled using Lie groups because they are so efficient. Yeah, it's really a universal language that you find in many, 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 many places. And yeah, it's fantastic, and that's why you would care. The correct answer to why you would care is I like it, but there's also the more objective answer. It's like a really efficient language, and you should literally see this as a language. So when we do the abstract theory, eventually it feels like learning a language, but it's actually really easy and much easier than the finite group picture, which you might be familiar with. You don't need to know much about finite groups to follow this lecture series. Essentially, you don't need to know anything about them. But if you have seen the picture of finite groups are more difficult than Lie groups. And the way this turns up is that the theory of finite groups doesn't have many results. The theory of Lie groups is like pretty large, actually. Okay, and as usually, I also like to study applications. So here, so I told you before that the standard examples, the main examples, the key examples of Lie groups are matrix groups. And kind of interestingly, the mathematical formulation of the standard model, which you can just Google, you find it on Wikipedia, is essentially using Lie theory. Right? So it's modeled by the special unitary groups in this case. So again, it turns up everywhere. And I probably need, I know I sound like a broken record, but let me just repeat that. I don't think actually the world is modeled after Lie groups. I think people model the world after Lie groups, using Lie groups, because it's such an efficient language. So I'm not really saying the particle physics, the particles of the world are Lie group type objects. It's more like we try to understand them using Lie groups. In any way, kind of turns out that this is one of the main applications, and you will find that in physics a lot. Yeah, so a lot in physics and a lot in math, but you also have real world applications like robotics or symmetry machine learning. Yeah, a lot of real world applications. Again, maybe because of people try to use things that work very well to explain the world. Right, it makes kind of sense. Anyway, so where's this series going? So here is a track along the east coast of Australia, which is a very long trail. If you want to walk it, it's a very, very long. It starts here in Victoria and ends in Cooktown, or the other way around, depends how you want to do it. And learning Lie theory is like walking this trail. Right? It's a very long trail, so it will take you a long time. But it's totally fine to just walk a little piece. Maybe you just want to go to Canberra or something. So you can only walk a little piece. Totally fine. But anyway, it's a long series. It's a long, but the series will not even capture all of Lie theory. I'm only focusing on 3 things, essentially. But learning Lie theory is a long trail. So essentially, we learn foundations. Representations are very, very efficient. But SU2 is my favorite example of all time. And I will just use it all the time to just explain kind of what's going on and why it's so famous and why people like it so much. And at the very end, I will also talk about the general theory, which I think is kind of a nicer way of doing it. A lot of people start by explaining the general theory, so like learning the language and then showing you how to actually speak it. I'm trying to do it the other way around, which is not super original. You see kind of the sources you see online are kind of doing it half-half. Some of them start with the abstract theory and then go to concrete examples. Some of them start with concrete examples and go to the abstract theory. I'm more the type of person who starts with concrete examples and goes to the abstract theory. This is what you will see in the series. So hopefully this will be reasonably interesting for you. And yeah, as I said, if you don't like linear algebra, but you made it this far, please don't keep on watching. If you don't like linear algebra, it won't be... I'm not 100% sure. I'm not going to tell you what is fun for you, obviously. But I doubt that it will be fun if you don't like linear algebra. Anyway, I hope you enjoyed this video, and I also hope to see you next time.